Today's lecture is on types of side distances. So let us understand what is overtaking side distance or OSD. So if all the vehicles travel on a road at the designed speed, then there should be no need of any overtaking. Okay, so in fact all the vehicles do not move at the designed speed, and this is particularly true under mixed traffic conditions. So what happens is, in such circumstances it is necessary for the fast moving vehicles to overtake or pass the slow moving vehicles. So it may not be possible to provide the facility to overtake the slow moving vehicles throughout the length of a road. So in such cases, facilities for overtaking the slow vehicles with adequate safety should be made possible at frequent distance intervals. So what is the meaning of OSD? So OSD is a minimum distance open to the vision of the driver of a vehicle intending to overtake slow vehicle ahead with safety against the traffic of the opposite direction is known as the minimum overtaking side distance. It is also called as the safe passing side distance. So as you can see in this figure here, the OSD is a distance which is measured along the center of the road, which a driver with his eye level of 1.2 above the road surface can see the top of an object. Okay, 1.2 meter above the road surface. So what are the factors on which the minimum overtaking side distance required for safe overtaking? So it depends on various factors such as the speed of the overtaking vehicle or overtaken vehicle and the vehicle coming from the opposite direction. Next, it depends upon the distance between the overtaking and the overtaken vehicles. Then the skill and the reaction time of the driver. Then the rate of acceleration of the overtaking vehicle and the gradient of the road. So coming to the analysis of overtaking side distance, so the figure shows the overtaking of a vehicle A, okay, traveling at a designed speed, and another slow vehicle, that is B, you can see here, on a two-lane road with a two-way traffic. This is a two-lane road with a two-way traffic. Now the third vehicle, okay, that is the C, third vehicle C comes from the opposite direction. As you can see here, third vehicle C comes from the opposite direction. So the overtaking may be split, okay, up into three operations. So thus dividing the overtaking side distance into three parts, that is D1, D2 and D3. So what is D1? D1 is the distance traveled by overtaking vehicle A during reaction time T second of the driver from the position A1 to A2. Okay, that is your D1. So what is D2? D2 is the distance traveled by the vehicle A from A2, okay, to A3, A2 to A3 during the overtaking operation in time T seconds, and D3 is the distance traveled by the oncoming vehicle C from C1 to C2 during the overtaking operation of A in T seconds. So certain assumptions, okay, certain assumptions are made in order to calculate the values of the D1, D2 and D3. So it may be assumed that the vehicle A is forced to reduce its speed to the speed VB of the slow vehicle B and moves behind it, allowing a space S, okay, allowing a space S till there is an opportunity for safe overtaking operation. So the distance traveled, okay, distance traveled by the vehicle A during this reaction time is D1 and is between the position A1 and A2, as you can see in this figure. It is between the position A1 and A2. This is the distance D1. So D1 will be equal to VB into T, that is the reaction time, which equals to 2 into VB. Now from the position A2, the vehicle will start accelerating, shifts to the adjoining lane, it will overtake the vehicle B and shifts back to the original lane ahead of B in the position A3 in T seconds. So the straight distance between the position A2 and A3 is your D2. As you can see here, A2 and A3 is your distance D2. So the minimum distance between the position A2 and B1 may be taken as the minimum spacing, okay, of the two vehicles while moving with the speed VB. So S will be given as 0.7 VB plus 6. So if the time taken by the vehicle A for the overtaking operation from the position A2 to A3 is t seconds, so the distance covered by the slow vehicle B traveling at a speed of VB meter per second will be given by small b, which equals to VB upon t. So your distance d2 will be b plus 2s. Okay, so d2 will be VB t plus at square upon 2. Okay, b is your VBT. Okay, and your s is your at square upon 2. Okay, so you're substituting in this equation here. So your capital T will be square root of 4s upon a seconds. Okay, and your d2 will be VBT plus 2s in meters. So next, the distance traveled by the vehicle C moving at a design speed v meter per second during the overtaking operation of vehicle A, that is during the time t, is a distance d2 between the position C1 and C1 to C2. So d3 will be v into t. So your OSD will be d1 plus d2 plus d3. Substitute the value of d1, d2, d3, which is VBT plus VBT capital T plus 2s plus VT. So your OSD will be 0.28 in kmph. It is given as 0.28 VBT plus 0.28 VB capital T plus 2s plus 0.28 VT. So your VB there is the speed of the overtaking vehicle. Small t is your reaction time, it is 2 seconds. V is the speed of the overtaking vehicle or a design speed. Capital T is 14.4s upon a. S is the spacing of the vehicles and a is your acceleration. Next is the overtaking zones. So let us understand what is overtaking zones. So it is desirable to construct the highways in such a way that the length of the road visible ahead at every point is sufficient for safe overtaking. So this is a practicable, and there may be stretches where the safe overtaking distance cannot be provided. So in zones where overtaking or the passing is not safe or it is not possible, the sign posts, okay, should be installed indicating the no passing or the overtaking prohibited before such restricted zone starts. So the zones which are meant for the overtaking are called this overtaking zones. So the sign posts should be installed at sufficient distance in advance to indicate the start of the overtaking zones. So the distance may be equal to d1 plus d2 for one-way road, and for two-way roads it is d1 plus d2 plus d3. So the minimum length, okay, the minimum length of the overtaking zone should be 3 times the safe overtaking distance. It is 3 times the d1 plus d2 plus d3. So as you can see in this figure here, this distance is your overtaking zone, that is the minimum length, which is 3 times the OSD. This is a SP1, that is a sign post for overtaking zone ahead. SP2 is your sign post, it is end of the overtaking zone. This region is your OSD. Okay, this region is your OSD. So it is desirable, okay, the length of the overtaking zone is 5 times the overtaking sight distance. So remember, the length of the overtaking zone will be 5 times the OSD. Now let us see a problem. Let us see this. Let us read this. So the speed of the overtaking and the overtaking vehicles are 70 and 40 kmph on a two-way traffic road. So if the acceleration of the overtaking vehicle is 0.99 meter per second square, we need to calculate the safe overtaking side distance. Then next we have to mention the minimum length of the overtaking zone, and third is we need to draw a sketch of the overtaking zone and show the positions of the sign post. So what is given in this problem is the speed is given, speed over the overtaking and the overtaken vehicles, okay, that is 70 and 40 kmph. Acceleration is given 0.9 meter per second. We need to calculate the safe overtaking side distance. Let us see how to do this. This is the solution of this. So first one is we need to calculate the overtaking side distance for a two-way traffic. Overtaking side distance for two-way traffic okay, so this is equal to d1 plus d2, which equals to d3. So assume the design speed is the speed of the overtaking vehicle A. Assume the design speed as the speed of overtaking vehicle A. Okay, so V is given to us as 70 kmph. Okay, in the problem it is given V is 70 kmph. We need to convert in meter per second. So V will be 70 upon 3.6, which is 19.4 meter per second. Okay, so VB is given to us as 40 kmph. It is overtaken vehicle speed, that is VB 40 upon, we need to convert this, so 3.6, okay, 40 upon 3.6, which is 11.1 meter per second. Okay, next is acceleration. Acceleration is given to us, it is A is 0.99 meter per second, is 0.99 meter per second square. Okay, so d1 is a distance traveled by vehicle 1, so d1 will be VB t. Okay, take t as 2 seconds, so assume t as 2 seconds, adopt t as 2 seconds. Okay, so VB we calculated as 11.1. okay, so VB is 11.1, t is 2, so this will be 22.2 meters. Okay, so d2 is VBT, d2 is VBT plus 2s. Okay, so your s is given as 0.7 VB plus 6, which is equal to 0.7 into 11.1 plus 6, which is 13.8 meters. Okay, so calculate t. T will be square root of 4s. Okay, formula is 4s upon a, which is 4 into 13.8 upon 0.99, so which is 7.1 47 seconds. Okay, so your D2 will be VBT plus 2S. Okay, so D2 is 11.1 plus 7.47 plus 2 into 13.8, which is, it comes out to be 110.5 meters. Okay, next we need to calculate D3. So D3 is VT. D3 is VT. Okay, that is equal to 19.4 into 7.47, which equals to 144.9 meters. Okay, so your OSD will be D1 plus D2 plus D3, which equals to 22.2 plus 110.5 plus 144.9, which is equals to 278 meters. Okay, so next is told we need to calculate the minimum length of the overtaking zone, that is your part B. Minimum length of the overtaking zone will be minimum length of overtaking zone will be 3 times your OSD. Okay, so 3 times D1 plus D2 plus D3 for a two-way traffic. Okay, that is 3 times 278, which is 834 meters. Then desirable length of the overtaking zone will be 5 times the OSD, right? So desirable length of overtaking zone will be 5 times your OSD. Okay, that is 5 times 278, which is 1390 meters. Okay, next we need to draw a sketch of the overtaking zone and we need to show the position of the sign posts. Let's draw here. C is the details of the overtaking zone. This is your C. Okay, this is the center. So this is your overtaking zone length, overtaking zone minimum length, which we found it as 384 to this length is 834 to 1390. Okay, this is your OSD. That is, we have found it as OSD 278. Okay, this is your OSD. That is 278. Okay, this is your SP1, that is signpost overtaking zone ahead. Here also we have SP1. This is your SP2. What is SP2? Signpost end of the overtaking zone. This is also your SP2. Okay, so SP1 is the signpost overtaking zone ahead, and SP1 is signpost overtaking zone ahead, and SP2 is the signpost end of the overtaking zone. Okay, so SP1, what is SP1? Signpost overtaking zone ahead, and SP2 signpost end of overtaking zone. Okay, so this is the end of this problem here. Next is the horizontal alignments. Okay, so the design factors to be considered in the horizontal alignment are the design speed, radius of the circular curves, the type and the length of the transition curves, the super elevation, and the widening of pavement on the curves. So the alignment should enable consistent, safe, and smooth movement of vehicles operating at design speed. Okay, so the improper design of horizontal alignment of roads will necessitate the speed changes, resulting in increased vehicle operation cost and higher accident rates. Okay, so design speed. So the overall design of geometrics of any highway is a function of the design speed. So the design speed is a main factor on which a geometric design elements depends. So the side distances, the radius of the horizontal curve, the super elevation, extra widening of the pavement, the length of the horizontal transition curve, and the length of the summit and the valley curves are all the dependent on this design speed. Okay, so the speed standards of a particular class of roads depends on the classification of the terrain through which it passes. So according to this terrain classification, such as the plain, the cross slope will be around 0 to 10%. So rolling it is around 10 to 25, mountainous 25 to 60, and for steep it is greater than 60. So these are the design speeds on the rural highways. Okay, according to this road classification, we have the different design speeds in kmph for various terrains. Okay, for national and state highways, for this plain ruling it is 100, for rolling it is 80. Okay, for mountainous it is 50 for ruling, and for steep ruling it is 40. So you need to go through this table. Next, design speed. So the recommended design speeds for different classes of urban roads. For atrial roads it is 80 kmph, then for subatrial it is 60 kmph, collector streets it is 50 kmph, local streets it is 30 kmph. So coming to the horizontal curve. So a horizontal curve is a curve in plan to provide change in the direction to the center line of a road. So now when a vehicle it will traverses a horizontal curve, the centrifugal force will act horizontally outwards through the center gravity of the vehicle. Okay, so the centrifugal force developed will depend on the radius of the horizontal curves and the speed of the vehicle negotiating the curve. So this centrifugal force is counter-reacted by the transverse frictional resistance which is developed between the tires and the pavement, which enables the vehicle to change the direction along the curve and to maintain the stability of the vehicle. So the centrifugal force P is given by this equation, that is W V square upon GR, where P is the centrifugal force and W is the weight of the vehicle, R is the radius of the circular curve, V is the speed of the vehicle, and G is acceleration due to gravity. Next is the horizontal curves. Okay, so the ratio of the centrifugal force to the weight of the vehicle, that is P upon W, is known as the centrifugal ratio or the impact factor. So this centrifugal ratio is equal to V square upon GR. So this centrifugal force which is acting on a vehicle negotiating a horizontal curve, it will have two effects. One is the tendency to overturn the vehicle outwards above the outer wheels and tendency to skid the vehicle laterally outwards. Okay, so we have the overturning effect. So the overturning moment due to the centrifugal force is P into H. So the centrifugal force that tends the vehicle to overturn the outer wheels B on the horizontal curve without the super elevation, as you can see in this figure. So the overturning moment due to centrifugal force P will be P into H. So this is resisted by restoring the moment due to weight of the vehicle W and is equal to V B upon 2, where H is the height of the center of the gravity, as you can see, gravity of the vehicle above the road surface, and B will be the width of the wheel base. So the equilibrium condition for overturning will occur, okay, when PH equals to VP upon 2. So P upon W will be B upon 2H. So this means that there is a danger of the overturning when the centrifugal ratio P upon W or V square upon GR will attain a value of B upon 2H. Next is a transverse skidding effect. Okay, so transverse skidding is a centrifugal force has a tendency to push the vehicle outwards in the transverse direction. So if the centrifugal force P developed exceeds the maximum possible transverse skid resistance due to friction, the vehicle will start skidding in the transverse direction, as you can see in this figure. So the equilibrium condition for the transverse skid resistance will be P equals to FA plus FB, which equals to FRA plus RB, which equals to FW, where F is the coefficient of friction between the tire and the pavement surface in the transverse direction, and RA and RB are the normal reactions at wheels A and B. Okay, now to avoid the overturning and lateral skidding on horizontal curve, okay, so the centrifugal ratio should always be less than B upon 2H and F. Okay, so the vehicle will overturn on the outer side before skidding if the value of B upon 2H is lower than F. So the relative danger of lateral skidding and overturning depends on the whether F is lower or higher than B upon 2H. Okay, so with this I come to the end of this lecture.